All right, so I wanted to make a video going over an old worksheet that I gave you a long time ago over tilted axis problems, and specifically problems 10 and 11, and we'll see how much we get through here. But just getting at the idea of how to draw a tilted axis problem and practicing drawing that triangle. So let's look at this example. It says a box is on an incline of 35 degrees. And so let's go ahead and draw that. So we'll draw an incline here, kind of like we have in the lab in class. An angle of 35 degrees. I think maybe I should have made this a little larger, but that's all right. And we have, I'm going to give that angle some color. Whoa. Make the size of that a little smaller. All right, that should work. And then we have a box that's sitting on the incline. And we can go ahead and put a dot on the box. A little cross hatching. Okay. And then go ahead and label some forces, right? So we know that if this box is just sitting here on this incline, that there's got to be a force of gravity, and it's got to point straight down. There's got to be a force from the incline pushing back on the box, and this is going to be force normal. It's going to point normal, or 90 degrees to the surface. Here's the surface, this inclined plane. Maybe we can make that maybe we can color it blue, right? The surface. And so we have to point 90 degrees to it, and that's normal. So this would be a normal. This would be a normal. These purple lines that I'm drawing, and so that's why the normal force points like it does. Okay, let's go ahead and label that. I'm going to use little lowercase n. And then there's a frictional force stopping it from sliding. So this frictional force has to point up the incline. And furthermore, since it's stopping it from sliding, it has to be static friction. So I'm going to call this FF. I'll put an R on there. I don't have to. It could just be FF. But we definitely want the S on there because the S tells us it's static friction. And static kind of reminds me of stationary. So it is something that is stuck, something that is not moving, so we call it static. Okay. Which is interesting because you think about static electricity, why that's called static. Maybe electrons that aren't moving, right, is a way to think of it. They're just sitting on an object is charged up, and then you experience that static electricity, obviously, by if you touch an object that has a static charge and you receive that charge, but maybe the idea being that the charge is not moving, right? It's just sitting there on the object. Okay. So, all right, we have these three forces, but they don't agree. They don't follow the up is positive y and right is positive x rule of logic, right? Which is normally this right here, right? Like we normally see in this class. It doesn't want to agree with that. And so what we do is instead of resolving these two into components, Fn and force, friction, static, we actually just change the one on the bottom, Fg, because what we'll do with our axis is we'll tilt this. We'll tilt it so it looks like this. So now the y direction, positive y, is actually agreeing with normal. And negative y points like this. And positive x will point up the incline. Negative x will point down the incline. So we just took the normal axis system and tilted it. So I'm going to erase that. We don't need that anymore. And we're going to use this new one. But now we see force gravity doesn't get along with this because force gravity points like this right here. And so that orange arrow, that orange vector. So what I'm going to do is I'm going to solve for force gravity in its components or its parts. So what we'll do, let me erase that orange vector, and we'll draw two orange dotted lines here that will represent this purple force gravity vector. Now the way to do this, to draw these dotted orange lines, is that one of them always opposes force normal. All right, that'll be FGY. So go ahead and draw that in. This is how I always do it, and this is why my triangles always look the same. And when I look at your guys' triangles, they're you know, sometimes just kind of whatever, you know, just kind of making triangles with whatever lines you can find, and that's not good. So think of it this way. One dotted line opposes force normal. It's opposite it, because we know there's no acceleration in this new y direction. Another one is going to make this block slide down the ramp. And so we're going to draw it. We're going to draw it down here. Let me see. I lost my, okay. I had the eraser on. I was erasing the black dotted line. We're going to draw it down here, pointed down the incline. Something to note, hold on. Something to note here is that FGY and FGX are head to tail. And when you add the two orange dotted lines, you get FG, the purple line. So I just want to mention that because it is important, right, that we're seeing vector addition here. Okay, so we have this right triangle, and now you can just go ahead and label, right? But a hypotenuse and an opposite and adjacent. We can label a hypotenuse. We can't label the op and adjacent yet because we don't have an angle. What we have to remember is that the 35, this lime green angle that's hanging out to the left of our triangle, is actually going to be in our triangle, and it's going to be right here. So let's go ahead and color that. That is 35. Right there. So now we can do some SOHCAHTOA, because now we have a theta is equal to 35. We have, and we can reference these sides compared to theta. So across from 90, I always start there first, across from this red 90-degree angle is actually our hypotenuse, which is FG. And FG will always be the hypotenuse. And remember, FG is mg. That's going to come back here in a second. We're going to need that. So FG is weight, force gravity. mg is 9.81, baby g, times the mass of the object in kilograms. All right, we'll talk about that in a second. Across from 35, across from theta, is our opposite, which is FGX. Let's go ahead and label that. And next to theta is our adjacent. So if you have to pause the video there to understand why these are the hip, op, and adjacent, make sure you do that, because it's super important you see why that's true. Why FGX, which X is usually an adjacent, is actually an opposite. Pause the video, look at the right triangle, figure it out. And this is actually this is so important to get this triangle right, because everything stems from it, like the rest of this problem. So, all right, I'll let you pause it if you need to. All right, let's get started again. So the next step here is they ask us to draw the components of FG, label 90 degrees theta in the component vectors, and then they say FG of X is equal to and FG of Y is equal to. So we need to solve for FG, FGY, and FGX. I think we can actually, I don't think we have to do much solving for FG. Let's go ahead and I think we got room over here. FG is always mg, which FG is a weight. So it's important to remember that. When we say force gravity, FG, we mean a weight. Now, we're going to multiply the mass in kilograms by 9.81 meters per second squared. which is true of any object on the planet Earth. You multiply its mass in kilograms by 9.81, you get its weight. Not in pounds, but in newtons. And 4.44 newtons is a pound, so you can change it. You can make the conversion. What did I want to say here? Fg is mg. So are we given the mass? We should be. It says the force gravity of the box is 500 newtons. So they're actually telling us what force gravity is. We don't have to calculate it. So that's nice. But I could guess what the mass is if I really wanted, right? This is 500 newtons. If I had to guess, m times 9.81, which is approximately, 9.81 is about 10. So if this is about 10 right here, approximately, right? What times 10 is 500? What times 10 is 500? And you should be saying 50. So approximately, right? So if I had to guess for the mass of the object, it would be 50. But once again, we didn't need to know it. 50 kilograms. We didn't need to know it because they just told us 500 newtons. So we are okay. Let's go ahead and add that in our triangle. I'm going to write it in purple again so it goes with this FG right here. That is my hypotenuse, 500 newtons. Okay. FGX and FGY. We'll do a little SOHCAHTOA here. Let's say we want to find FGX first, which is an opposite. So we're going to use sine. Let's go ahead and write that down. All right, let's go ahead and plug in our angles. 35, plug in our opposite, which is FGX. And the hypotenuse we said is FG, but FG is the same as, hold on. So we have that, but we said FG is the same as, I think the problem told us it's 500, right? So we can plug in 500 right here for FG. All right. So to solve this, let's just multiply both sides by 500 newtons to get FGX alone. So we'll multiply this side by 500 newtons and this side by 500 newtons. They cancel. This 500 newtons cancels this 500 newtons. And we can go ahead and rewrite what's left. I'm going to go ahead and move FGX to this side just because I like the way it looks better. Let's go ahead and get the calculator going here, making sure we're in degrees, not in radians. Radians are nice for some classes and for physics sometimes, and degrees are nice other times, so you got to make sure you know when. 500 sine 35. I should be in Norman rads, so I got to get out of radians. I have to hit mode and change it. Let's see, degrees. Yeah, in physics we sometimes use radians, so I change mine somewhat often. All right, so if I do the math there, it's 286.79 units. This is a force, so it's going to be in newtons. All right, so good. There's our answer for FGX. What about FGY? Well, FGY, if we look back here, it is an adjacent, so we're going to do a little cosine. This is why it's important you memorize your SOHCAHTOA formulas. You really shouldn't have to look them up. So if you're still having to look them up, you either need to do more practice or you just need to sit down and memorize them. I always like the idea that you memorize things by practicing instead of just memorizing just to memorize. So, what I mean by that is every time we do these problems, make sure you're writing it out. Cosine 35. Okay. And that way you memorize it just based on doing your homework. And that's a pretty good way to do it. The adjacent is FGY. The hip is FG. But we did say earlier that FG is the same as 500 newtons. Multiply both sides by 500 newtons because we want to get FGY alone. Cancel, cancel. And we can go ahead and rewrite. All right. And so we're taking the cosine of a smaller angle, under 45 degrees, smaller between 0 and 90. And so cosine does a little bit better with this, so expect a larger answer. Sine does better with the larger angles, 45 to 90 degrees. I'm getting about 409.5758 newtons. All right, so far so good. Let's see what's next on the agenda here for this problem. I think we're getting towards the end. They then say, what is the normal force equal to, and what is the net force on the box? So now that we know FGX, FGY, and FG, right? We know FG up here. We said FG is the same as 500. Granted, it was given to us in this problem, but in some problems, it's not going to be given to us, and we have to multiply our mass in kilograms by 9.81. They then say, what is the normal force equal to and the net force on the box? Okay, so let's solve for the normal force. And I think technically here we could solve for friction as well. So let me grab another piece of paper. All right, and what we're going to do is the same thing we always like to do with problems like this, is once we free body diagram, we then like to sometimes do a redraw step. Redraw steps aren't necessary, but it can clean up the problem. There are 3 forces acting on this problem. Although it looks like there may be 5, there's only 3. They are right here, Fn, force, friction, static, and Fg. 3 forces. FGY and FGX are not new forces. They're just parts of FG. So there's just 3 forces on the block or the crate. What I like to do in a redraw is just look at, well, what is really happening? Meaning, we know, even though there's only 3, that there's more going on than that, right? That the crate gets affected by it differently, right? Because we use a tilted axis. So in the redraw, I just like to point that out. So what we see is actually happening is something like this. Let me see if you can see that. I probably should have picked a different color for these forces. So in the redraw, this is kind of an optional step, but I like it. What we do is we only draw the components. So we end up drawing all 4, or 4 forces in the redraw. So really there's only 3 that exist. Our other problem looks like there's 5, but our other drawing. But the thing is, I don't like how Fg of x is kind of just floating around in the middle of nowhere. So in the redraw, what's nice about it is you can see what's going on with these forces. Like what is actually influencing the crate. Now the crate is just sitting there. So we know if it's just sitting there, we call this situation equilibrium. There are 3 instances in this class of equilibrium. In equilibrium, we know the acceleration is equal to 0. And so we like to look for equilibrium situations. And in these equilibrium situations, we're going to have AX equal to 0. meaning the acceleration in the x direction, or up or down the incline in this case, and the acceleration in the vertical direction into the sky or through the plane is also going to be 0. So that's what we mean when we say equilibrium, that these accelerations are equal to 0. Because I like to be a little more specific than just saying a equals 0, right? We like to say ax or ay, because sometimes that's not going to be true, right? Like maybe ay will be 0, but the block will be speeding up down the ramp and we'll have an ax. That is a number that is not 0. So sometimes this won't be true. So here are the 3 examples of equilibrium. The first one is the object's just sitting there. And if something's just sitting there, in physics, we like to say it's at rest, right? I forgot the word at. Dang it. It's at rest. So that's the first example of equilibrium. The second one is it's moving at a constant velocity. And this showed up in the lab, where we were pulling a block at a constant velocity. And so the idea behind equilibrium then means that it's not speeding up or slowing down, right? So when we say the acceleration is equal to 0, we mean not speeding up and not slowing down. Because we all know speeding up is accelerating, but slowing down is also accelerating, which is weird to think about. Acceleration is changing your speed, changing your velocity. Velocity is speed in a direction. All right, and then the final one, the object, and this is, think brick lab here, the object just begins to move. Because even though once it moves, it did accelerate, we are freezing it. It's almost like we took a picture of the object right before it moves. So that is the instant we care about. We care about right before it does move. So the object just begins to move. We consider that still equilibrium. Oops, I don't need to write is equilibrium. We know that. So 3 instances of equilibrium. All right, so which one are we dealing with in this problem? We are actually dealing with an object just resting or sitting right there, or sitting there at rest. So we're dealing with situation 1 here. So we know that the acceleration is equal to 0 in the x direction, this way, right? And in the y direction, this way. So in both of these new tilted directions, there is no acceleration in this problem. Okay. So let's go ahead then and look at this. And so what we can say is we like to write Newton's second law, and we can say for the x direction, so we like to work in independent directions here, we can say the sum of the forces in the x direction is equal to ma in the x direction. So when we do this, we know the acceleration is equal to 0 because we just said that ax is 0. It's not accelerating up or down the ramp. But we do have forces acting on it up and down the ramp. We have friction static up the ramp and Fg of x down the ramp. All right, and we can see that force friction static is in the positive x direction, right? So I'm saying that this right here is the positive x direction, and Fg of x is in the negative x direction. So if that's true, I can then come down here and write force friction static as a force that I'm summing here, and Fg of x as another force I'm summing, but it's negative, so it gets a negative sign. So I apply that sign right there. Whereas force friction static is in the up the ramp or positive x direction, it stays positive, or I don't write a sign at all. The mass, I don't know, it's about 50. I'm just going to leave it as m right now. I could write 50 there. But here's the thing. We're going to multiply 50 by 0. And that's just 0. See? So it didn't matter if I wrote the 50 or not. All right, so we have this. And we can then show one final step. Even without using numbers, right? Don't have to put numbers in yet. We'll just move FGX to the other side and see what we proved here. These cancel over here. We proved that the friction static is equal to Fg of x. This is because there was no acceleration, so the two forces end up balancing out. And this is all about the x direction. Now, we showed a second ago that Fg of x is the same as what? You remember? 286, let's see if I can zoom, 286.79. So we're just going to bring that 286.79 down here for Fg of x. And look what we just proved. That friction static is 286.79. Now you might say, well, I can see that. I knew that just by looking at this. This obviously looks balanced. Okay, but we backed it up with math is the idea. And this allows us to do tougher problems when we use math like this. Let's look at the y direction. We can say the same thing. And we know the same thing about the y acceleration. Here's why. Force normal, right, points up into the sky. The crate's not speeding up into the sky or slowing down into the sky. This one points through the surface. The crate's not speeding up through the surface or slowing down into the surface. So, acceleration's got to be 0. The mass times 0 is just 0. So this entire side on the right is 0. On the left here, we're adding two forces. Fn points up, so it's positive. Fg points down, so it's negative. But it's not just Fg. I got to be careful. It's Fgy. Right? This is a part of gravity. It's not just gravity. We can go back and look at that, right? Fgy points in the new down. You might say, well, Fg pointed down. Yeah, but we don't care about that anymore because we got Fgx and Fgy. They represent Fg. So we only are looking at these four right here. All right, so this happens right here. Fn is positive, Fgy is negative. We then kick Fgy to the other side just by adding Fgy to both sides. We can go ahead and cancel right there and then rewrite. And we just proved Fn equals Fgy, which means that we can go ahead and go back up to the top, get the value for Fgy, and we'll know Fn. Right? So what is that value? 409.58 newtons. 409.58. All right. Okay. So, all right. So we're good. Let's go ahead and write some numbers here, just so you can see something. All right, so the last question is, what is the net force on the crate? And what we can see is that if we look at the x direction up and down the incline, that this right here is going to be a positive 286 up the ramp. And this right here down the ramp is going to be a negative 286. Hopefully you can see that. I'm talking about this right here and this right here. And if we look at the vertical direction, this is going to be a positive 409, and this is going to be a negative 409. talking about this right here and this right here. So those balance. So positive 409.58 plus negative 409.58. This means that there's the F net, the net force, the sum of the forces, right? What is force net? F net is equal to the sum of the forces. And we're seeing that that's going to equal 0. So for an object in equilibrium, here's what's true. F net in the x direction is equal to the sum of the forces in the x direction, which is equal to max, which is equal to 0. And that makes sense because think about it, right? Ax is 0. So if this is 0, 0 times m, then everything else is 0. Then that's 0, then that's 0, then that's 0. And the same is true in the y direction for an object in equilibrium. Because once again, ay is 0. So this is 0, so this is 0, so this is 0, so this is 0. All right. So the net force on this crate has to be 0. All right. Good. We'll call it there. Make sure you're writing all this down on a separate sheet of paper. And that's it. Have a good day.